what we've been doing is we've been working with what we call the normal distribution. And one of the things that I want you to understand is that we sort of alluded to it at the end of last class. It turns out there's this big, awesome theorem called the central limit theorem. And again, the mathematics behind it are pretty advanced, and we're not going to get into details of it in this class. This is an introductory course. If you want to learn about the specifics of the heavy math, you take higher level courses. But what it does tell us is that it tells us that many things in nature can show and exhibit behavior that is distributed normally. So that's kind of the sort of the gist of what you want to take. And we're going to show you how we can work with that right now. So again, let's set the stage for the scariness that is what we've been talking about. So go back to our first week of class, and we talked about this very fundamental experiment. We want to measure the heights of everybody on the planet. Right? We know we can't do that. It's impossible. So what we then say is, okay, what if we take a subset of people on the planet? Well, how many do we need to have accurate results? Do we have too many? Do we waste too much time and get too many that was unnecessary? Or did we get lazy and not get enough to get a representative sample? So what we need to do is we need to decide what is the appropriate sample size that we need to get information about the population. Okay, so one idea would be to take advantage of what we call the central limit theorem and say, okay, the central limit theorem says what we can do is we can look at a bunch of different samples. And then if we study those samples and we average them out in some sort of way, then things become normal. And so this is not just limited to, I don't want to say become normal, that's a bad way. They exhibit behavior that seems to be normal. So anyhow, does anybody have a question, comment about what we've been doing? No? All right. Oh, someone has to say something. Yeah, we can do that right now. Let's look at an example. Let me pull it up. Luckily, I have it here. I think I do. Homework, the most recent one. Why can't I find it? And don't forget, the homework is technically due tonight. Okay, yeah, so you want to do something like number 2. So really the big skill, the skill you need is number 2. You need to know how to find probabilities. Because you can't do any of the other problems until you can do problems 1 and 2. And then all the thing that matters in problems 3 and on is how do you formulate it in terms of problem 2. That's the goal. And usually it's pretty self-explanatory. Once you've done 1 or 2 of them, it's not, again, once you get over the hump of 1 or 2 of them, it's not terribly difficult to do the rest. But so suppose we want to do something like this. So let's assume we have X is a normally distributed random variable. and it's going to have a given mean and standard deviation or variance. So let's say the mean is, how about 28? And let's say its standard deviation is, I don't know, how about 6.3? What we like to do is let's determine something. Let's determine the probability that X is between, let's say, 23 and 27. So how do we do this? There's a few ways you can do it. As I said, one way is the old-fashioned way where you take your random variable X and we transform it to a standard normal variable using a formula. And then we go look it up in the back of the book or a table on the internet. So let's do it two ways. So solution method one, we know that Z is X minus mu over sigma.
Oh, Grady, I hate to be a pain. Can you go back real quick just for the one side?
You're not a pain. Yeah, take your time. Let me know.
I just need to take a picture of it.
You need to take a picture.
Yeah, so I can write it down.
Forever that way. Digitally lasts forever.
Yeah, you're good then.
All right, so we need to convert to Z. Now, here's the thing. In the previous problem, we have two X values we're interested in. So we are interested when we're we're interested when we're less than 27, but greater than 23. So I need to figure out what Z values I need to be between. Do we understand that? So I have to compute this twice. I have to do it for the first X, the smaller X, and also the larger upper bound. So for X, say less than 27, we have, so let's say Z equals 27 minus mu. What was our mu? Our mu was, I already forget. Now I got to go back. What was it? 28 and then over 6.3. And so if you go to a calculator and get that, you get -1 over 6.3. Which we can round to -0.15. Say 58. I know we should round up, so we'll round up to 9. And then for 23 less than X, we have to find the other Z value. So we will solve it with 23 minus 28 over 6.3. Double check my math. Did I do 23? Yeah. And then this becomes -5 over 6.3, which if you go to a calculator, you get Z equals -0.794. So what I did is I looked at the two X values I wanted to look between, and I transformed it so now I know what Z values I'm looking at. So what is my corresponding problem? My corresponding problem is the following, or not corresponding problem, but what I've changed my problem to. And so one way of writing this is the probability that our random variable x is between 27 and 23 is the same thing as the probability that z is somewhere. Well, what is it? Well, the smaller number is 0.794 and the larger is 0.15. All right, 794. I can't have no memory. 794 and 15. Now, looking this up in a standard table is not as straightforward as the other ones, because this is not the just less than. If we draw the area of what we want, we have to use our axioms to figure out how we're going to handle this. So what I'm going to do is I'm going to draw the picture. We don't need to be exact, but what we can do is let's sketch the region. So if I come over here, I'm going to scale it differently because I know I'm in the negative side. And what are my two numbers that are important? Well, my numbers that are important are negative 0.794 and then say negative 0.159. Those are the numbers I'm interested in. And I know that I have a standard normal variable now, so I know my highest point, my mean is here, so it's going to look something like this. And so what I'm interested in is I am interested in this region here. That's the area that I need to determine. I have a question about this. Now, here's the issue. Depending on what table you look up, the table is not going to give you this specific area. You have to use some reasoning skills. So here's what I mean by depending on what table. So suppose we go to the internet. Do I have it? I guess I need to open one. Come on, Google. What are you taking so long? What's happening? There we go. So let me Google for the standard normal table. It's one way you can Google it. And let's think about our values. So this is the table we've used before. Now we don't have to use this one, we can use any one, but let's look at the table value. If you look at the top, it's telling you how it's computing these values. It's the area to the left of the z-score. Well, that's not what we want, right? We want some area to the left, but we want to cut it off. So we now have to reason what this area is if we want to use this particular table. Do you understand what I'm saying? So this particular table, if I annotate it, if I look at this table, what it's doing is it is taking the standard normal guy, and wherever your z is, it's taking the area all the way to the left, everything. But we don't want that. We want it between two z values. So we need to reason, how are we going to handle this? Does everybody understand the point I'm making? Our scenario doesn't go all the way forever and ever and ever. It stops. So we can reason this a few different ways. We can find the probability that you go up to 0.159 and then subtract off the tail piece. That's one way of doing it, right? So we could reason it as follows. So we could we could say, okay, this probability, this red region, let me write it in English right now instead of scary symbols. So we could reason as the red area equals area up to negative 0.159 minus the area we don't want, which would be the area up to negative 0.794. Does that make sense? So I'm going to say the red area, this red area is everything, subtract off this piece. I'm not saying this is the only way to solve the problem. This is one way to do it. Just like when I leave here today, I got lots of ways I can drive home. Hell, I might get brave and just close my eyes and see what happens. That ain't the best method. And it surely ain't the best method for me to drive to Erie and then turn around and go home if I live south of the city. And I'm not saying this is the best method. I'm saying this is a method. How do you find methods you like? You practice and then you figure it out. Okay, so this is one way we might reason this. And so let's go with it. This is equal to the probability that Z is less than negative 0.159 minus the probability that Z is less than negative 0.794. Now, both of these are the areas that we want, at least on the table we're using. So after we do this calculation on the next page, I'm going to show you a general thing of what we just did. And I don't want you to think of it in terms of I don't want you to think of it in terms of scary symbols. What I'd like you to think about is in terms of your 5th grade brain, shapes and colors. Right? So right now we got scary symbols, and I understand that. But part of being an adult in a university is doing math with scary symbols. I don't make the rules. I wish more people liked these scary symbols. But one thing you need to realize is there ain't a human being on this planet that just was born understanding what the hell they're seeing on the board right now. No one just understands it. I don't care how smart they are. Anybody who understands what these symbols are worked at understanding it. So what happens is most of us peasants who take a class like this for the first time, we just think we're stupid and not math people because we don't like scary symbols. And then you have your mom or your Uncle Bill or someone who told you your whole life that some people are left-brained and some people are right-brained and some people like art and some people like math, all a bunch of BS that we tell people not to have their feelings hurt. When really what we should tell people is, yes, this ship is hard. And if you don't work at it, you ain't gonna learn it. That's what we should tell kids. It's hard. Not that they should do something else because their brain wasn't born to do it. Ain't nobody's brain born to understand what the hell this means. Nobody's. Anyhow, I digress. Believe it or not, I sucked at this stuff too once. And for all you know, I still suck at it. I'm just lying to you. I can't help but look at your drink. I keep thinking that's like, well, you can imagine what I think it is. I don't know why. You got like a drug test you got later or something? I'm kidding, of course, but I'm not. Ben Roethlisberger's here today. This is good. Are you excited that the Steelers won?
Yeah, we're off for a great season.
Yeah, you sure? Oh, yeah, I say you. We are. Very good. I was excited yesterday. I said I like to watch. I love that sports is back. Gross enough, I wore this shirt yesterday, if that isn't disgusting, right? I smell good. This is my Steelers shirt, black and gold. I should get one of these made with the Steeler logos. Learning. All right. All right, so the first thing we got to do is we got to go look at this negative 0.159. And let me go back and double check that I actually have the right numbers. I think I do. Yeah, okay. 794,159. So that's what I'm going to do. I'm going to go to my little Z table, and it's 159. So remember, I got to go over here to 159, right? So I need the 15, but no, I don't, because this is 1 point. So I got to keep going. I need down here to 0.1. And then I have to go to the top column because I need my 0.9, or excuse me, 0.5. So it's going to be this column right here. I have my cursor on. And so what I get is 0.1, and then 5 is 0.44. So let me zoom out and just make sure I did this correctly for the people viewing at home. Maybe I could cheat this way. Yeah, here we go. Let's cheat this way. So here, I'm going to go down here. So I need the negative 0.1. So I need this row. And then I need, it's 0.15, so then I need this column. And so the answer that I seek is the number I seek is 0.44038. So I'll go write that in. All right, now I have to subtract off the next one. Well, the next one is Z less than negative 0.794. Now this is where your head's gonna hurt. So let's go back to our thing, and we need 0.7. Well, look, there ain't no 0.7. There's just not. By the way, let's look at the graph. If let's go to Desmos. Let's look at the graph. Remember what this is. So it's a scary creature, is it not? What was the graph? It was y equals. Does anybody remember what it was? We know there's an e raised to something. It's negative 1/2, we think, x squared. But remember, there were some constants out there. Does anybody remember? There was a pi in there. There was a square root of 2. You're telling me you don't have this memorized? I'm just kidding. You can look it up in the book if you'd like. But the constant out front was 1 divided by the square root of 2 pi. And so what I want to draw your attention to is, let's sort of switch. Let's leave this here and let's go to. So if I sort of switch my scale so we could see this, notice what happens. Way down here. Yeah.
Would that be 1.5? Because I can't really see it.
Which one?
Like the
Up in here? This?
Yeah. Right
Yeah, it's 1/2 in front. But honestly, like I said to you before, I'm not gonna test you on this. You don't need we wrote this formula down once. You ain't gonna have to write it down again. Now, if you want to learn it, then of course you have to, know how to graph and stuff. But don't stress about that. Notice that what is the area? What are we interested in here? What are we interested in? I'm gonna write something scary down again. You're gonna be mad at me, and I feel bad. What we're interested in is the following. We are interested in the area under this thing. Don't have heart failure. So we are interested in this piece. We are interested in, what was it, 7? I already forget. My brain, honest to goodness. 794 and 159. 794 and 159. Forgot my minus sign. So this is the region that we want to compute. Right? So let me remind you what I'm doing. I want to know this region. So what I'm doing is I'm going to find it all the way up to here. And then I'm going to subtract off this white region all the way back. That's what I'm doing. All right, so now we have to go to this point, which of course is 794. Is that what we did? Oh my God, get this out of here. 794. So we found the first one. And now we have to find the second one. So where is 0.7 at? Well, here's our 7. And then we have to go to the second column, which was 7, 9, right? So that would be all the way over here. So it's 0.21476. I believe, yeah. 0.21476. And so now if I go to my calculator and plug this creature in.
I might have missed something on that. So why did you have to like go into the graph and try to graph it before?
Why did I didn't have to. I was just trying to show you a nicer picture then.
Oh, okay.
So the question you're asking is why did I go from here and take time to show you that on Desmos?
Yeah.
Only reason I did that is I wanted to show you a prettier picture of this. That's all. But I'm going to go back to that in a second to give you a more clearer picture of sort of my reasoning here. Does that make sense?
Yeah.
All right. So if we do this, then we get the probability that it's 0.22562, or if you'd like, 22.56%. So this was the long drawn out way of doing this problem. Now, of course, we're not going to pretend this is the most efficient way, because as I showed you last class, this can be done in an instant if you know how to use the proper software, calculator software. But what we should do is we should ask ourselves, does this even make sense? And it seems to make sense. So let's go back to the original problem. Imagine what we do. We said we had a normally distributed random variable with, say, mu 28 and sigma 6.3. So let's concoct an example in our head. Let's say we make, how about we make metal rods and people buy them? I don't know. We sell them to Home Depot. And we want to know what the average weight of or the length of our metal rod is when we cut it by a machine. And so let's suppose the average length is 28, say, inches of our metal rod, and then there's a standard deviation of 6.3. So one way we can interpret the bottom, that would be find the probability that if we randomly picked one of these rods, that its length would be between 23 and 27 inches. Well, that probability is not very high. We got 22%, and that seems to agree with this model that we're not even near the mean, and our mean is spread out pretty wide because of this sigma 6.3. This is a fat one, if you will. Okay, so you should try to, and that might not have done anything for you there. You might still be confused, and that's if you're supposed to be confused right now. It's not easy to learn, but you should try to ponder scenarios or what these numbers mean. What do these symbols mean? All right, it's worth noting that we're going to do this again in a second on a computer, and we better get the same answer, at least close to it. Maybe we have a different rounding error than they do, right? Because we're rounding things, correct, aren't we? You know, when we went from X to Z, we rounded. All So it's possible that the computer gives us something slightly different. So let's go to our normal calculator. So we'll go back to the internet. And like I told you the other day, you could just do a normal calculator. And we'll probably get, here's one. Here's the one we did the other day, I think. Yeah, we used this one. Now, this one is a standard normal. So if we wanted to use this calculator, we would have to go and convert to the z's anyhow, right? So let's go back to the other calculator we used. If you remember, we used another one that didn't require us to convert to z. You don't even have to spell it right. See, it just knows exactly what we're doing here. So here's another calculator. Now here it even lets us specify our parameters. What was our parameter? 28. What was our standard deviation? 6 point, was it 3 or 8? I forget already. 3. And then we'd like to know what was between two things. What were we wanted to be between? We wanted to be between 23 and 27. And there's our original picture. And look what number we got, 0.2232. What number did we get the long old-fashioned way? 0.2256. Now we we're accurate at least in the tens and ones position, but we rounded different than that. But we're still confident we did it correctly. So again, I'm not going to tell you which calculator to use. I don't care how you do it. I really don't. You want to be a show off, go write your own code and make your own. Some of you are like, huh? Go be a computer programmer. And then when you go to a job interview one day and they say, what can you do? And you can say, look what I did. Instead, you'll just sit there like a zombie and say, oh, I have a college degree. And they're like, yes, so does millions and millions of other people, right? What can you do? What are your skills? I don't know. Anyhow, does anybody have a question about this? So it's important to understand that the reason our answer is different than theirs, albeit slightly, is because we rounded at some point. Now, there isn't an important thing we didn't talk about because I don't think it's important in this class. It's important in the real world is there has to be conventions on how we round. And sort of every community has their own conventions of how they do things. I'm not going to waste time taking points off from you in an intro to stats class on how you round. So I'm not making a big deal about it. But the textbook tells you their convention. And so conventions are important. It's just not important in my opinion here. But to talk about what I mean by conventions, when I went and got these numbers, I rounded a certain way. How many of these digits did I need? Should I have rounded it the tenths or the hundredths? You know, when should I have rounded? You notice I carried 3 digits. I rounded. Maybe if I would have rounded just 2 digits, I would have gotten the same answer that they got, right? Do you understand what we're saying here? I just don't think that's important right now. Now, these things are important in the real world. If you're analyzing a study on some sort of medicine, then you need to understand how to round properly, right? You need to understand things like significant figures and significant digits. Maybe you've learned about that in a psychology class or a statistics, or excuse me, a chemistry class. I mean, there are important things. Imagine anything that a human does, you're introducing air. If I'm reading a gauge or I'm measuring, by default, there's going to be air. The same way 2 of us might read a gauge, we might read it differently. How do we round? So we need to have conventions for things like that. It's just this, in my opinion, this class isn't the place to talk about that. So, sorry. So let's now say method 2. How did we do this problem method 2 solution? Here's what I did. I Googled normal calculator, and I didn't even spell it correctly. And plugged in. and we got the probability that X was between 23 and 27 was 2232. So again, our answer differs slightly because of rounding, how we round it. Any comments, questions? Ethan, does that answer your question? You asked it. Are you comfortable with that? Yes, no, maybe so.
I guess I have a question with
Yeah.
how do you use the calculator that computes it to Z?
You'd have to first find your Z. So let's go to that one. So suppose we went to that calculator, this one.
Yeah.
Okay, so now this calculator is not as sophisticated. All right. So what you'd have to do is you'd have to do exactly what we did. You'd have to first do the 0.159. And you'll see it gives you 0.563. So if you go back to our work, oh, I hit the wrong button. Sorry. I forgot the negative sign. That would be bad. Yeah. I don't like this calculator. It's annoying me. So you get 0.437, which if you look at what we did, that's what we got. Only we rounded differently, right? So this is actually a good point. Notice we used 0.44038 because when we read our table, we were using different values. So that's a very good question here. Why are we getting different? This is a good for extra credit. Why is the value Z less than negative 0.159 that we got? Why is that differing so much from what they got, 0.437? What if we did the other one? What was the other one? 749? I think that was it. Oh, God, we have to delete this.
It was 794.
794. And 0.214. Once again, now that one agrees to 3 decimal places, but here we didn't agree. So we ask ourselves, maybe we made an error here. Right? Maybe we go back to our table, 0.159. So what if I go back to my table? 0.1 and then 5. What was 0.15? Well, 5 is this column. Once again, it's 0.44038. So there's a clear discrepancy between this table and the calculator.
Is that just a rounding issue, or is that something else?
It seems to me that's the case. But it is an important thing to notice nonetheless. 0.437, again, 0.437 and 0.44, I mean, it's a rounding issue for sure. So the question you might, I mean, look, if we rounded 0.437 to the nearest hundredths, then you get 0.44, right? So what I'm saying is 0.437, if I round it up, becomes 0.44. So we're not terribly off, but it's clear that the table and the calculator are doing things differently. Does that mean one's right and one's wrong? No, it's a rounding thing. I mean, we could, if we wanted, we could look at another table. What if we went to, instead of that website, we used, let's use this website. I don't know. It's a YouTube. We ain't gonna watch a video. Give me. You gonna show me this or what? Oh my Lord, this video is gonna actually show you how to do it. What a time to be alive. Oh my God, look, this is a great resource, but we don't want that though. I want a table. I need a correct one. Does this one work? All right, here's one. Just gonna give me a PDF, or are you gonna take me to these stupid websites? Sometimes you just gotta throw a PDF in. Oh my God, why are they making this so difficult for us? This is the same one we just used. What kind of criminal activity is this? All right. Here we go. All right, so here's a table. So which one did we have? The 0.1? We need the negative side of it. Oh, this is down. I'm having a heck of a time with this today. Can I get one picture that is going to work for me? Oh my Lord. Why can't we just find a simple one? Give me a look, this is teaching you how to do it. There you go. That's so cute. Here's a table. Here we go. Let's see what this table. So 0.159, right? 0.15 right down here. See, this one's 0.4404. So even that's different, right? So we got 3 different results. And by the way, the reason you get this, and this is, if you've never had calculus, it's hard to explain this, but this area that we're computing, the way you compute this is you have to approximate it using these, so the mathematical operation that gives us this area is what's called integration. And in order to compute this number, you have to do some rounding at some point, approximation. So that's why we're seeing this happen. Does anybody else have a question about that? That's a good example. I like how we got 3. They were all the same, but they weren't the same, right? I mean, relatively speaking, the answers we got were the same number, but there was slight difference in all 3 of them. So that's something that should be noted. Any other questions about this problem? How about anything else on the homework while we're at it? Going once, going twice. All right. Let's move on then in the moments that are remaining. All right, so back to the central limit theorem. So we did some, we wrote some things down about this last week. In particular, we said, imagine we have these samples. We called them X1, X2, X3. And we said, all right, these samples are what we call sample means. So here's a way to think about this. So sometimes we are interested in what we call in an individual data point. And that was what the most recent homework is about. Other times, we are interested in a sample mean. So this goes back to the height thing I've been yapping about over and over and over again. If I take a sample of the world's population of adults and measure their height, the average height is a sample mean there. It's not the population mean. And so if I want to ask questions like, what is the probability my sample mean is close to the actual mean, then I have to distinguish between these two things. Do we get that? So it's one thing to ask information about you, an adult, and your height, but it's a different question to ask about a sample of the population. So here's what I mean. Let's illustrate it. So research suggests, so I'm just making up some example here. Someone does a study, right? We do research, we do an investigation. So research suggests that a person, and we'll assume a working adult, I don't know, commutes on average let's say 27.8 minutes to work. We assume commute times are normally distributed. We don't know this, but we'll assume. With standard deviation of, let's say, 5.9 minutes. Now, I'm going to ask two questions, and I want you to understand that I'm asking two different things, and I want you to understand why we're asking two different things. So question one. What is the probability a randomly selected person commutes longer than 29 minutes. If 50 people are selected at random, what is the probability the sample mean will be greater than 29? Do you understand the distinction? There is a big distinction here. The first question is asking about one random data point, one person in this case. The second problem is asking about a sample mean. Question one is along the lines of the stuff we just did before and what we did last week. Question two is different. It is asking about sample mean. And the central limit theorem, this big, scary mathematical theorem, says that we don't study that problem the same exact way as we studied the previous ones. There's a slight difference. For one, we solve the problem just like our recent homework. The probability that X is greater than, what did I say, 29. And of course, this, if you used your Z table, you would say Z equals, 28 minus 29. What wasn't 28 exactly? What was it? 27.8. And then the standard deviation, which, what was that? It's 5.9. So this would be the probability that Z is greater than this number, which I have to go to a calculator. So here you end up getting negative 0.2033. And so you can look this up. Turns out this formula does not work when we're looking at sample means. It's not accurate. It doesn't work in theory and it doesn't work in practice. And so we need a different formula. And when I say formula, what I'm referring to is this transformation from X to Z. So for 2, we need a different formula. That is a result of the central limit theorem. So this formula, remember, if we're taking a sample, what we're really asking is we're asking how is our sample mean differing from the theoretical or population mean? So we use this creature divided by, not sigma, it's very close, but it's not, sigma over the square root of n, which is our sample size. So this is a scary, scary formula. Lots of fractions here. Yes. Square root of n. Right, so we're going to write this again on the next page, but just so we're all clear. Look, we're using context here. Remember, we haven't used x bar in a while, but what was x bar? X bar was, by definition, way back in the beginning of the semester, that was our sample mean. And then what is n? Well, n is our sample size. If we go back to the statement of the problem, we said 50 people. That is our sample, 50. So here, x is the sample mean. N is the sample size. And of course, in this problem, the sample size was 50. We told you that. And then what are we thinking our sample mean is? Well, we asked, what's the probability that it was greater than 29, right? So here, this is 29. And so Z is 29. Well, excuse me. Is that what we use, 29? Yeah. And then what was our commute thing? Wait a second, did I mess that up? We got an error here. Hold the phone. We had this backwards here. What was our, okay, so what we were asking that we were going to be greater than 29. So this is backwards. Hold the phone. Remember, the mean that we were given was 27. We were given that. We were given 27.8 was the mean. So what we should be having, the way this should be 27.8, and this should be 29 minus that. Right? So this is not negative. This should be this. All right. Sorry about that. Right, because our x, we're asking it's greater than 29, so this is x minus mu over 5.9. Now, the same thing here, this would be 29 minus our mu. What was our mu we were interested in? Well, if you go back to the problem, 27.8. So the only difference here now is we're not just dividing by sigma, we're dividing by sigma over the square root of n. So what was sigma? If you backtrack, sigma is 5.9. And so you can go to a calculator to figure this out, which is what I'm going to do. I can't do that in your head. I don't know. Maybe you can. So once I go to a calculator, what I end up getting is 1.43818. If I didn't make any errors. And so thus the probability that your sample mean is going to be greater than 29 is the same as the probability that this Z is greater than 1.43. And of course you can plug that into the or go look at it at the table, or you can go use a calculator, whatever you want. So this is a good place to stop. What I would really encourage you to do is think about the difference in both of these questions. We're going to give you a couple problems to do for homework. And of course, please ask about them on Wednesday, whether you chat it up or whatever. Does anybody else have any questions or comments before we go? Going once, going twice. All right, gang, thank you very much. I appreciate it. I will see you guys Wednesday. Take care.
Thank you.